This is the first image of the black hole event horizon. This is what we've been waiting for. This is on Live Science, Science Alert. Scientists reveal groundbreaking results from Event Horizon Telescope. So we're looking at history here. Astronomers have just released the very first direct image ever of the event horizon of a black hole. You can scroll and just go back up and look at it for a second, and before this, every image of a black hole was simulation or an illustration, an artist's illustration. But this is a photo. It was taken of the supermassive black hole at the center of a giant elliptical galaxy called M87, around 55 million light years away, and this thing is humongous, around 6.5 billion times the mass of our sun. And isn't it glorious? Well, it's the first result from the Event Horizon Telescope, a global collaboration that turned radio telescopes around the world into one giant telescope, expressly to find out what a black hole looks like in reality. Beautifully, it matches predictions dating back decades, and this is it. And we now know for a fact that the astrophysical objects that were just theory a mere 50 years ago are really what astronomers and physicists thought they were. Quote, "The confrontation of theory with observation is always a dramatic moment for a theorist," end quote. This is what astrophysicist Luciano Rezzola of Goethe Universität in Germany says. He says, "It was a relief and a source of pride to realize that the observations matched our predictions so well. It looks a bit like a blurry orange coffee stain, but here's what we're looking at. In the middle is the shadow of a black hole, as you can see there. And we can't actually see the black hole itself because its immense gravity does not allow any detectable radiation to escape, so it appears as an opaque space. Around it is this accretion disk, and M87 supermassive black hole is active, which means it's surrounded by a tremendous accretion disk of very hot swirling gas and dust that's slowly falling into the black hole, and the disk gives off a lot of radiation. Because the disk is rotating, it appears brighter where it's moving towards us and dimmer where it's moving away. This effect was predicted by Einstein's theory of general relativity. The image is not high enough resolution at this point to measure the rotation speed, but the EHT team could tell that it's rotating in a clockwise direction. Future analyses of the data, which are all being made publicly available, could reveal more details, such as how closely the image matches predictions of general relativity. It could also help astrophysicists figure out the mechanisms that produce the enormous relativistic jets that shoot from the black holes. Now, the three huge questions the black hole image did not answer for us. This is from Live Science, Rafi Letzer, staff writer. On the left, an image taken using the Chandra X-ray telescope at the same time as the Event Horizon Telescope made its picture known, a relativistic jet crossing the Virga A galaxy. On the right is the image of the black hole shadow from the Event Horizon's telescope. And on the left we have the Chandra X-ray. An international network of radio telescopes has produced the first ever close-up image of a black hole's shadow. This is the real, it's not the artist illustrations, which scientists reveal this morning, April 10th. The collaboration, called the Event Horizon Telescope, confirmed decades of predictions of how light would have behaved around these dark objects, and set the stage for a new era of black hole astronomy. Quote, "From the scale of 0 to amazing, it was amazing," end quote, said Erin Bonning, an astrophysicist and black hole researcher at Emory University who was not involved in this imaging effort. She said, "That said, it was what I expected." Now, the announcement, teased for about a week and a half in advance, managed to be both incredibly exciting, almost completely devoid of surprising details or new physics. Physics did not break down. No expected features of black holes were revealed. The image itself was almost a perfect match for illustrations of black holes we're used to seeing in science and pop culture. The big difference is that it's a whole lot of blurrier. Now, there were several important questions related to black holes that remain unanswered, unresolved. Bonning said, how do black holes produce their enormous jets of hot, fast matter? All supermassive black holes have the ability to chew up nearby matter, absorb most of it past their event horizons, and spit out the remainder into space at near light speed in blazing towers astrophysicists call relativistic jets. And the black hole at the center of the Virgo A, also called Messier 87, is notorious for its impressive jets spewing matter and radiation all over space. Its relativistic jets are so huge that they can fully escape the surrounding galaxy. And let's go to that down a little bit further down. We have the image of that right here. There it is. Okay, that's the jet coming out of the black hole. As you can see how huge it is. This is a 1998 Hubble image showing the relativistic jet escaping Virgo A. Now, physicists know the broad strokes of how this happens. The material accelerates to extreme speeds as it falls into the black hole's gravity well, and some of it escapes while retaining that inertia. But scientists disagree about the details of how this happens. This image and the associated papers don't yet offer any details. Figuring that out, Bonning said, will be a matter of linking up Event Horizon Telescope observations, which cover a fairly small amount of space, with a much bigger images of relativistic jets. While physicists don't yet have answers, she said, there's a good chance that they'll come up soon, especially once the collaboration produces images of its second target, the supermassive black hole Sagittarius A, at the center of our own galaxy, which does not produce jets like Virgo A's. Comparing the two images, she said, might offer some clarity. Now, how do general relativity and quantum mechanics fit together? Whenever physicists get together to talk about a really exciting new discovery, you can expect to hear someone suggest that it might help explain quantum gravity. That's because quantum gravity is a great unknown in physics. For about a century, physicists have worked using two different sets of rules: general relativity, which covers very big things like gravity, and quantum mechanics, which covers very small things. The problem is, those two rule books directly contradict one another. Quantum mechanics cannot explain gravity, and relativity can't explain quantum behavior. Someday, physicists hope to link the two together in a grand unified theory, likely involving some sort of a quantum gravity thing. And before the announcement was made today, there was speculation that it might include some breakthrough on the subject. If general relativity's predictions had not been borne out in the image, that would have moved the ball forward. During a news briefing from National Science Foundation, NSF, Avery Broderick, a physicist at the University of Waterloo in Canada and a collaborator on the project, suggested those sorts of answers might be coming. But Bonning was skeptical of that claim. This image was entirely unsurprising from a general relativity perspective, so it offered no new physics that might close the gap between the two fields, Bonning said. Still, it's not crazy that people hope for answers from this sort of observation, she said, because the edge of a black hole's shadow brings relativistic forces into tiny, quantum-sized spaces. We would expect to see quantum gravity very, very close to the event horizon, or very, very early in early universe, when everything was packed into tiny space, she said. But at the still blurry resolution of Event Horizon Telescope, she said, we are not likely to find those sorts of effects even with planned upgrades coming. Now, were Stephen Hawking's theories as correct as Einstein's? The physicist Stephen Hawking's greatest early career contribution to physics was the idea of Hawking radiation, that black holes are not actually black but emit small amounts of radiation over time. The result was hugely important because it showed that once a black hole stops growing, it will start to very slowly shrink from the energy loss. But the Event Horizon Telescope did not confirm or deny this theory, Bonning said, not that anyone expected it to. Giant black holes, like the one in Virgo A, she said, emit only minimum amount of Hawking radiation compared to their overall size, while our most advanced instruments can now detect the bright lights of their event horizons. There's little chance that they will ever tease out the ultra-dim glow of a supermassive black hole surface. Those results, she said, will likely come from the tiniest black holes, theoretical short-lived objects so small that you might enclose their whole event horizon in your hand. With the opportunity for up-close observations, much more radiation available compared to their overall size, humans might eventually figure out how to produce or find one and detect its radiation. Well, why would we want to produce a black hole? God forbid. This is so stupid. You know, sometimes I get so angry. How can you want to produce a black hole? Now, so what did we actually learn from this imaging? First, physicists learned that Einstein was right. Once again, the edge of the shadow, as far as the Event Horizon Telescope can see, is a perfect circle, just as physicists in the 20th century working with Einstein's equations of general relativity predicted. I don't think anyone should be surprised when yet another test of general relativity passes, Bonning said. If they had walked on stage and said that general relativity had broken, I would have fallen off my chair. The result with more immediate practical implications, she said, was that the image enabled scientists to precisely measure the mass of the supermassive black hole, which sits 55 million light years away at the heart of the Virgo A galaxy. It's 6.5 billion times more massive than our own sun. That's a big deal, Bonning said, because it could change the way physicists weigh the supermassive black holes at the hearts of other more distant or smaller galaxies. Right now, physicists have a pretty precise measurement of the mass of the supermassive black hole at the heart of the Milky Way, Bonning said, because they can watch how its gravity moves individual stars in its neighborhood. But in other galaxies, our telescopes can't see the movement of individual stars, she said, so physicists are stuck with rougher measurements. How the black hole's mass influences light coming from different layers of stars in the galaxy, or how its mass influences light coming from different layers of free-floating gas in the galaxy. But those calculations are imperfect, she said. You have to model a very complex system. And the two methods end up producing somewhat different results in every galaxy physicists observed, but at least for the black hole in Virgo A, we know now that one method is correct. Our determination of the 6.5 billion solar masses end up landing right on top of the heavier mass determination from the light coming from stars. Sarah Markov, an astrophysicist from the University of Amsterdam and a collaborator in the project, said in the news briefing. That does not mean that physicists will just move wholesale to that approach for measuring black hole masses, Bonning said, but it does offer an important data point for refining future calculations. If you'd like to join me on my Patreon account, you will hear content not covered by mainstream media. These riveting stories will be based on my research, and I will state my opinions and give my personal insight on diverse and controversial subjects and world events not covered by mainstream media, and not supported by YouTube guidelines. So whatever I have on my Patreon, most of those will not be on my YouTube channel. Please consider becoming a member today. More of the most significant and important videos will be on my Patreon channel. Your support helps me to continue my research and keeps this YouTube channel alive. And we depend on your support, your generous charity, because we help economically challenged families here in Athens, Greece, in Kapota, and we also help the young generation with university tuition and the community around our church. Thank you.